Welcome back to Toward AGI. AI's history is defined as much by failure as by progress. The AI winters, periods of disillusionment and collapse, nearly killed the field. But some kept going, quietly, relentlessly. Today, with the release of GPT-5, it's tempting to focus only on the breakthrough, but this moment is built on decades of resilience. The real story isn't just what AI can do now, it's what it survived to get here.
By the end of this episode, you'll understand why AI's roller coaster history holds the key to navigating its turbulent future. From winters that nearly killed the field to innovations now reshaping our world.
So, let's rewind to that Boston conference room in 1974. The air was thick with ambition. Researchers convinced machines would soon think like humans. Marvin Minsky himself had declared, just a few years earlier, that within a generation, AI would match human intelligence.
And yet, it didn't. Not even close. What went wrong?
The promise of early AI far outpaced its reality. Systems could play chess or prove theorems, but they couldn't generalize. The tech just wasn't ready. Then came the Lighthill Report in 1973, a bucket of cold water that shut down funding and froze momentum. The first true AI winter had begun.
Right, James Lighthill's infamous report. It slammed AI for overpromising and under-delivering. So what exactly did he say?
It was scathing. Lighthill argued that AI had made zero progress toward human-level intelligence. He dismissed much of the research as speculative and unproductive. And he wasn't entirely wrong. The field had overpromised, and now it was paying the price. Funding dried up overnight. Labs shuttered.
So the first AI winter wasn't just about money, it was a crisis of credibility.
And it forced a reckoning. Researchers had to ask, what can we do realistically? That's when you see the shift toward practical applications. Expert systems, for example, which could diagnose diseases or configure computer systems. No more grand visions of human-like machines, just tools that worked within strict limits.
It's almost like the field had to shrink before it could grow again.
That's the paradox of AI winters. They're brutal, but they prune away unrealistic expectations. By the late 1970s, the survivors were focused on solvable problems. No more chasing consciousness, just incremental progress.
Which, ironically, laid the groundwork for the breakthroughs we're seeing now.
Yep. The first winter taught the field humility. It showed that hype without substance is dangerous, and that lesson is still one we're still grappling with today. So if we fast forward from that first winter into the late 1980s, the field had clawed its way back. Expert systems were the new darling of AI. Picture this: sleek office towers in Pittsburgh, where teams at Digital Equipment Corporation were deploying a system called XCon to configure custom computer orders. It was handling tasks that used to take human engineers weeks in minutes.
That sounds like the kind of success story that would get investors excited.
Oh, it did. By 1985, corporations were pouring billions into expert systems. The Strategic Computing Initiative, a U.S. government program, had even earmarked funding to push AI toward military applications. The mood was euphoric again.
Wait, again? That's the key word, isn't it? Because we've seen this pattern before. High hopes then?
Then the cracks started showing. XCon could configure computers brilliantly, but only within a rigid set of rules. Ask it to handle something outside its narrow domain, and it fell apart. Scaling up? A nightmare. Maintaining these systems required armies of knowledge engineers to manually encode every rule. Costs ballooned.
So the very thing that made expert systems successful, their specificity, became their downfall.
Yes, and by the early 90s, the disillusionment was palpable. The Strategic Computing Initiative was quietly defunded. Venture capital evaporated. Sound familiar?
It's like the 1970s all over again. Overpromising, under-delivering.
But here's where history diverges. This time, the field didn't just retreat, it adapted. Researchers started questioning the whole paradigm. Maybe intelligence wasn't about rigid rules at all. Maybe it was about learning from data, and it didn't happen overnight. But the second winter forced a reckoning, just like the first one had. Out of the ashes came new approaches, neural networks, probabilistic reasoning. Ideas that had been sidelined during the expert systems boom suddenly got a second look.
So in a way, these winters aren't just setbacks, they're corrections.
Precisely. They strip away the hype and force the field to focus on what actually works. And here's the fascinating part. The researchers who survived the second winter, they were the ones who laid the groundwork for the deep learning revolution we're living through now.
It's almost like these winters are a necessary part of the process. Painful, but productive.
Think of it like forest fires. Devastating in the moment, but they clear out the undergrowth and make space for new growth. The second winter burned away the assumptions that were holding AI back.
and set the stage for what came next.
But here's the real question. If history rhymes, could another winter be coming, or have we finally learned how to weather the cold? So if we fast forward from those winters into the early 21st century, the landscape had changed entirely. Researchers weren't just tinkering with hand-coded rules anymore. They were building systems that could learn from data, systems that mimicked the layered structure of the human brain itself.
That's the deep learning revolution, right? The moment when AI stopped being told what to do and started figuring things out for itself.
Exactly. And it all started with something seemingly simple: image recognition. A neural network called AlexNet stunned the field at the ImageNet competition, classifying millions of images across 1,000 categories, and doing it better than anyone thought possible.
I remember reading about this. The previous best systems had error rates around 25%, right?
Correct. But AlexNet, it cut that error rate in half, 12.7%. And the way it did it was revolutionary, using convolutional neural networks, or CNNs. These weren't just layers of neurons, they were designed to mimic how the visual cortex processes edges, textures, shapes, building up understanding layer by layer.
So it wasn't just better, it was fundamentally different. Instead of being programmed to recognize specific features, it could discover them on its own.
Precisely. And that shift from explicit rules to learned features was the spark that ignited everything. Suddenly, machines could recognize faces in photos, detect tumors in X-rays, even identify wildlife in camera trap images. All because they'd learned to see.
But images are one thing. What about language? Understanding speech feels like a whole different ballgame.
And that's where recurrent neural networks, RNNs, came in. Unlike CNNs, which excel at spatial patterns, RNNs handle sequences. Think of them as networks with memory, where each step influences the next. By 2015, systems like Google's were using RNNs to transcribe speech with near-human accuracy.
That's wild. So while CNNs were revolutionizing vision, RNNs were cracking the code on language.
Yes, but these breakthroughs didn't come out of nowhere. They built on decades of work nearly abandoned during the AI winters. Researchers like Jeff Hinton, Yann LeCun, and Yoshua Bengio had been quietly pushing neural networks since the 1980s, long after most had written them off as a dead end. By 2016, the world took notice when DeepMind's AlphaGo defeated Lee Sedol, one of the greatest Go players alive. Go isn't just complex, it's intuitive. Humans play by feel, by pattern recognition. And yet AlphaGo learned to do the same, combining CNNs with reinforcement learning.
That's the thing that still blows my mind. It wasn't just calculating moves, it was developing something like intuition.
That's the hallmark of deep learning. It's not just brute force computation. It's about systems that learn patterns, adapt to new situations, and sometimes surprise us. Like AlphaGo's move 37 in Game 2 against Lee Sedol, a move no human would have made, yet it changed the course of the game. It wasn't just brilliant, it was creative.
Which raises the question, if these systems can surpass us in narrow domains, what does that mean for the future?
That's the tension at the heart of this revolution. On one hand, we have tools that can diagnose diseases faster than doctors, predict protein structures like Microsoft Research's AI2 BMD system, even write coherent text. On the other hand, we're still grappling with their limits, their biases, their unpredictability. Every breakthrough brings new promises and new pitfalls. The question is whether we've learned from those winters, whether we can temper our expectations while still daring to imagine what's next. Let's shift our focus from the broader history of AI to something more immediate: how these breakthroughs are transforming healthcare right now. There's a radiologist's workstation today where an AI system highlights a tiny nodule on a lung scan that human eyes might have missed.
I've read about algorithms outperforming seasoned doctors in detecting early-stage cancers, but how does that actually work in practice?
Take breast cancer screenings, for example. A study from 2023 showed that AI assistants reduced false negatives by nearly 30%. The system doesn't just look for tumors, it analyzes patterns in millions of historical scans, learning to spot anomalies that correlate with malignancy.
So it's not replacing radiologists, but augmenting them, like a second pair of eyes.
That's right. And here's where it gets even more nuanced. These systems are now tailoring their analyses to individual patients. Imagine a diabetic with a high risk of cardiovascular disease. AI can cross-reference their retinal scans, genetic markers, and lifestyle data to predict complications before symptoms appear.
That's personalized medicine in action. But what about drug discovery? I remember reading how traditional methods can take a decade and billions of dollars.
That's where AI is rewriting the playbook. Microsoft Research's AI2BMD system, for instance, simulates protein folding in days, a process that used to take years. By predicting how proteins interact, it accelerates the design of targeted therapies. One recent project identified a potential treatment for a rare genetic disorder in under 6 months.
Proteins are one thing. Can AI tackle broader challenges like antibiotic resistance?
Actually, yes. In 2024, researchers used AI to screen millions of chemical compounds for antibiotic properties. They discovered a promising candidate active against drug-resistant bacteria, one that had been overlooked in conventional studies because its structure didn't fit existing models. It's not about replacing human ingenuity, but expanding its reach. Take diabetes management. Continuous glucose monitors paired with AI can now predict blood sugar crashes hours in advance, adjusting insulin doses in real time.
That's life-changing for patients. But I have to ask, are we overlooking the risks? AI diagnosing diseases, designing drugs, influencing people. What happens when it gets something wrong?
A critical question. Algorithms trained mainly on one demographic can miss important nuances in others. That's why the best AI systems, like the Mayo Clinic's diagnostic tools, keep humans in the loop, treating AI as a collaborator, not a decision maker.
So the lesson from those AI winters applies here too. Temper expectations, focus on solvable problems, and build guardrails.
Yes, that's where the next frontier gets interesting. Agentic AI, systems that can autonomously design and run experiments. Imagine one that iterates through thousands of potential drug combinations overnight, then presents the most promising candidates to human researchers by dawn.
It's like having a tireless lab partner who never sleeps. But doesn't that raise ethical questions? Autonomous systems making high-stakes decisions?
Absolutely. That's why groups like the World Health Organization are stepping up to create guidelines for using AI responsibly in healthcare. Things like transparency, accountability, and fairness aren't just nice-to-haves. They're essential.
Breakthroughs open new doors, but each one forces us to confront fresh challenges.
That's the story of AI in a nutshell. From winters to springs, from hype to humility. The key is remembering that these tools are only as transformative as our ability to wield them wisely. So, we've seen how AI has transformed healthcare and scientific research. But let's zoom out. What's next on the horizon? Because right now, we're standing at the edge of 3 seismic shifts: agentic AI, physical AI, and sovereign AI.
Agentic AI, that's the idea of systems making autonomous decisions, right? Not just recommending actions, but actually executing them.
Imagine this, a 2026 corporate boardroom where an AI agent isn't just analyzing market trends, but negotiating contracts in real time, adjusting terms based on shifting regulations, even identifying risks human lawyers might miss.
But how do we ensure these agents don't go rogue?
That's the big question. Early tests are promising, like a pilot where AI agents manage supply chains for a major retailer. They reroute shipments around delays, negotiate with backup suppliers, and even predict demand spikes. But they always work within strict ethical boundaries, with humans keeping the final say on the biggest decisions.
Balancing autonomy with accountability. Speaking of autonomy, physical AI feels like another giant leap. Robots that don't just follow scripts but learn from their environment?
Think of a construction site in 2030. A robot with physical AI isn't just laying bricks, it's adjusting to uneven ground, changing its grip for wet materials, and even working alongside humans by anticipating their moves. These systems combine deep learning with advanced sensors to create what researchers call embodied intelligence.
That's eerily close to how humans learn. Trial and error, tactile feedback. But doesn't that raise concerns about job displacement?
Absolutely. A recent International Labor Organization study estimated that by 2030, physical AI could automate up to 30% of tasks in manufacturing and logistics. But here's the counterintuitive twist. In Japan, where aging populations face labor shortages, these robots aren't replacing workers. They're filling gaps humans can't.
So context matters. What's disruptive in one region might be a lifeline in another. But let's talk about sovereign AI. That term keeps popping up in policy debates.
Imagine a hospital in Nairobi using an AI diagnostic tool trained entirely on African patient data, not just repurposed models from the global north. That's sovereign AI in action. Systems built on locally controlled data, tailored to regional needs. The European Union's AI Act even includes provisions to incentivize this kind of data autonomy.
That's huge. It addresses the bias problem head-on, right? No more one-size-fits-all models.
Yeah, but it's not just about ethics, it's economics. Countries investing in sovereign AI infrastructure, like India's AI for All initiative, are betting that data sovereignty will be as strategically vital as oil was in the 20th century.
Which brings us back to those historical cycles. Every breakthrough creates new dependencies, new power dynamics.
The early AI winters showed us that hype without real progress can do serious harm. Now, as we face new challenges like autonomous decision-making, embodied robots, and data ownership, the question isn't just, can we build this, but should we, and if so, how? Stepping back from these cycles, the winters, the breakthroughs, the ethical quandaries. What strikes me most isn't just the technological evolution, it's the resilience of the field itself.
It's like each AI winter was a tough but necessary reset, trimming away the dead ends so the field could grow stronger and smarter.
The same hype that nearly derailed AI in the 70s and 90s also fueled the ambition to push forward. What's surprising, though, is how peer-reviewed studies now underscore something unexpected. The most enduring innovations often emerge from periods of constraint, not abundance.
Like neural networks, dismissed for decades before becoming the backbone of deep learning. Makes you wonder what's currently languishing in today's academic margins that might define the next breakthrough.
As agentic and physical AI evolve, they reshape our culture. Their autonomy, creativity, and even mistakes challenge how we understand work, responsibility, and what it means to be human. If history teaches us anything, the future of AI will be shaped not by those chasing the next shiny breakthrough, but by those who face its storms with clear eyes, steady hands, and unwavering resolve.